All right, so for modeling using quadratic functions, we're actually going to look at one specific example, but quadratic functions, the nice thing about them is that they can be used to model lots of actual data and lots of actual situations, even more so at times than linear functions can. For instance, we have the situation that says Jason jumped off a cliff into the ocean in Acapulco while vacationing with some friends. His height as a function of time could be modeled by the function h of t equals negative 16t squared plus 16t plus 480. So this is going to be the important piece, our function. Says where t is the time in seconds, so that's good to keep in mind what these represent, and h is the height that Jason's at in feet. So it says how long does it take Jason to reach his maximum height, and how long does it take him to actually hit the water? So if you're thinking about the trajectory of a person, of a ball, of anything that's basically what we would call a projectile motion, which if you're in physics, you may study a little bit, but when you're talking about projectile motion, the nice thing is it always follows, because of gravity, it always follows this parabolic shape. It's always a parabola shape. So if you think if I have some grass over here, and I took a football and I kicked the football, it would follow, and you think about a kickoff in an NFL game, it follows this parabola type shape. So different things affect the equation we use to model it. Maybe the height. So Jason's jumping off of a cliff. He's not like the football is on the ground, or you might be on a building, shooting something off, or even standing and throwing something from a height. So how fast you throw it, from what height, those things are going to affect what your overall equation looks like in the end. But if you think about how long does it take Jason to reach his maximum height? So let's pretend this parabola shape here on the right side is actually Jason's trajectory. So his maximum height, while you're looking at this parabola, his maximum height was also quantities we've already looked at. His maximum height, we're really talking about the vertex. So we really want to know, where's the vertex in Jason's trajectory here? And how long does it take Jason to hit the water? Well, what would Jason hitting the water be? I mean, if he's hitting the water, you think his height, h, is going to have to equal 0. Where does the height equal 0? Well, that's when we're at the roots of the equation, the roots or the x-intercepts. So those are the quantities we're looking for. We're just taking what do we know about parabolas and kind of applying it to a certain situation. So how long does it take Jason to reach his maximum height? The first thing we want to find is the vertex. So the vertex in this equation is in standard form. It's going to be, we take the negative b value, so we're going to find the vertex, negative the b value over 2a, so negative 16 over 2 times negative 16. So negative 16 over negative 32 looks like our x value is 0.5. Our x value in this case, really we should be saying this is t. And it says how long does it take Jason to reach his maximum height? So our vertex is at 0.5 or 1/2, comma, the t value, the h value. If we wanted to find the h value, we just plug that in. So negative 16 times 0.5 squared plus 16 times 0.5 plus 480. We simplify that. We get negative 16 times 0.25 plus 16 times 1/2 is 8 plus 480. All together, we're going to have 484. So our vertex is at 1/2, comma, 484. What's that really stand for? So besides just finding the vertex, we need to know what it stands for. It's the x value, which is t in this case, and the y value, which is h for this particular problem. So what do these stand for? It's half a second, and because that's what the x value stands for, and 484 feet because that's what the y value stands for. So it says, how long does it take? Well, it takes half a second to reach the maximum, to reach the max height, which is 484 feet. So using the vertex, using the roots, using the characteristics that we know, we can relate them to this problem. So how long does it take to hit the water? Well, we need to find the roots of this equation. So to find the roots, we're going to use the quadratic formula. And so I'm running out of room a little bit here. Let me get rid of this. There we go. That gives us a little more room to move. Okay, so roots are x-intercepts. We're thinking either factor. Try number one would be factoring. Try number two would be quadratic formula. Looking at this equation, I'm going to have to take negative 16 in order to factor. Negative 16 times 480. I'm not doing that. That looks pretty ugly. We could factor it. Might take you a little more effort than you want. I'm going to suggest on problems like this, just go ahead and do the quadratic formula. So negative the b value over b squared, or sorry, plus or minus square root of b squared minus 4 times a times c, all divided by 2 times a. So if we simplify that, we get negative 16 plus or minus square root of 16 squared is 256. Negative 4 times negative 16 times 480 is plus 30,720 and divided by negative 32. So negative 16 plus or minus the square root of 3976 over negative 32. And when we take that square root, thinking that works out pretty nicely, it's negative 16. I'm going to go up to the top here. Negative 16 plus or minus 176 over negative 32. So our solutions, finding our roots, we have negative 16 plus 176 over negative 32, and we have negative 16 minus 176 over negative 32. Those roots work out to be, the first one as negative 5, and the second one as positive 6. So you're thinking your roots are these points. So if I kind of graphed this cliff situation, this is how many seconds have gone by. This is the height. If I graph Jason jumping off of this cliff, he's got two roots. We've got a root at 6. We've got a root at negative 5. Which one do we really care about? We got to remember, what do these numbers represent? They represent the x values. The roots are the x values. They represent how many seconds. So we really only care about the 6. That's the only one that really makes sense. So how long does it take Jason to hit the water? It's going to take him 6 seconds because that's the root. And you can see kind of along your trajectory. Here's where Jason started. You may notice that value where Jason starts would be the y-intercept. There's his max height. The question about his max height had to do with the vertex. And then there's where he hits the water. And that's the root. So the points that we've been finding the past 2 days have relevance to an actual situation. To sketch it out a little more clearly, if we draw in our parabola, it's going to look something like this. The starting point, the vertex is the maximum height. The starting point is the y-intercept. and the end point, or in other words, hitting the water, it's a root or an x-intercept. So to kind of give you a sketch, kind of relate that parabola shape to an actual situation. So we'll be talking about situations like this and others that can be modeled with quadratics tomorrow.